Okay, welcome everybody. Today we're gonna talk about combining transformations and do an application problem. These are just the same examples that we went over in class on Wednesday. Just wanted to maybe run through these examples again, give everybody a chance to maybe pause the video, maybe try and get caught up. So, combining transformations, we're going to start with this function g of theta equals 3 sine of 1/2 theta plus pi over 2, and then outside the parentheses minus 1. Okay, now before finding your phase shift, your period, your amplitude, and your midline, what you're going to do is you're going to write this function g of theta. Okay, not sure where I lost everybody there, but again, here's a function that's a transformation of the graph of sine theta. Okay, now first of all, I'm not sure where I lost everybody, but I'm going to draw a fundamental cycle of sine. So this is going to be the graph of sine theta. And sine has maximum and minimum values, positive 1 and negative 1. The period of sine is 2 pi. And then whether it's sine or a transformed function, you're going to always break up your period into fourths when you graph your fundamental cycle. Sine starts at 0. Let me change colors. Sine starts at 0. Increases to positive 1 at pi over 2, 0 at pi. Negative 1 at 3 pi over 2. Sorry, I'm writing on top of my labeling for the axes. Okay, so there's a fundamental cycle of sine. Before transforming this function, you need to write it in a more useful form. We're going to write this as g of theta is 3 sine, factor out the 1/2 inside the parentheses, and then what you'll end up with is theta plus pi, and then a minus 1. So now what we need to do is we need to find the period, the phase shift, the amplitude, and the midline. Okay, so first of all, for the phase shift, the value of b, capital B, is the opposite of the sign in the parentheses. So where I'm looking at right here is right inside these parentheses at the theta plus pi. Okay, the sign of b will be the opposite of the sign that you see in the parentheses, so b is going to equal negative pi. So that is a phase shift. A shift of pi units left. Number 2 is to find the period. The value of capital A is 1/2. So the period P is taking the period of sine, dividing it by A, and the period of our transform function. Okay, one of its fundamental cycles will happen on an interval of length 4 pi. Okay. Step 3. Okay, since C equals 3, that's going to be, well, technically the absolute value of C. If it was negative, you'd take its absolute value. That would be the amplitude. So that's the distance from the middle value to either the maximum or minimum value. And 4, the midline is given by the horizontal line y equals negative 1. Okay, and I got this because, or if you like, since capital D is also minus 1. Okay. So there are 4 important characteristics right there. Okay, so what I'm going to do is I'm going to get rid of some of this. I'm going to summarize some of this on a different slide, and then we'll go ahead and sketch a graph of G. Okay, so down in the bottom left corner now, the phase shift is minus pi. That's where the fundamental cycle begins. A cycle is traced out over an interval of length 4 pi, which is the period. The amplitude is 3. That's the distance from the maximum value to the midline, or the midline to the minimum value, and the midline or the middle value of this function is y equals negative 1. Okay, so I'm going to start sketching a graph of this function. Our phase shift is going to, well, let's do this. First I'll do 1, 2, 3 tick marks up, and I'll do 1, 2, 3, 4 tick marks down. So that's negative 1, negative 2, negative 3, negative 4. And then up we're going 1, 2, 3. Since your phase shift is minus pi, I will start by labeling minus pi on the negative theta axis. If I go a fourth of the period, I get to 0. Another fourth of the period brings me to pi. Another fourth of the period brings me to 2 pi. And finally, a full way through the period, starting at minus pi, will bring me to 3 pi. I will sketch in my midline at y equals negative 1. That gives me the middle value of the function. And then now what I'll do is, comparing this, our cycle is going to look just like the fundamental cycle of sine. So starting at minus pi, that's where the fundamental cycle begins. Sine starts at its middle value, sine starts at its middle value of negative 1. Okay, and then since the amplitude is 3, when you go a quarter way through the period, you're going to go up 3 units to positive 2. Okay, halfway through the period, you're back on the midline. Another quarter way through the period, you're going to go down 3 units from the midline and get negative 4. And then finally, all the way through the period, another quarter period, you're going to be back at the midline of negative 1. And there's a sketch of one cycle of the function g of theta. And then I could just keep adding pi on the horizontal axis, and then over intervals of length 4 pi, which is the period, we just sketch copies of this graph. Should also be careful and make sure I label the theta, or the horizontal axis, as the theta axis. Okay, so example 7, we're going to find a function of the form h of theta equals c cosine of a times the quantity theta minus b, and then outside the parentheses plus capital D. So we need to look at this graph. Since we're trying to find a transformation of cosine, I will try to find a cycle of this graph that has the same general shape as the graph of cosine. So again, as I usually do, I'm going to sketch a fundamental cycle of cosine, my parent graph. So here's theta, period of cosine is 2 pi, and I will split that period up into fourths, so intervals of length pi over 2. Here's negative 1, here's positive 1, and then a fundamental cycle of cosine, you start at the maximum value of 1 at 0, you decrease through 0 at pi over 2, halfway through the period you're at negative 1, 3/4 of the way through the period you're at 0, the middle value, and then back to the maximum value at 2 pi of positive 1. And this is a graph of cosine of theta. Now if you look at the graph of h of theta, starting at the point 0, 1, you will see a cycle that has the same general shape as cosine of theta. And then another thing I like to point out, the minimum value is negative 3, the maximum value is 1, so the midline is going to be the line y equals negative 1. Okay, now if you look this cycle, it starts at x equals 0 and ends at x equals 1, so the period equals positive 1. The phase shift since our maximum value starts at a value of theta equals 0, the phase shift is going to be 0 units. Okay, that's going to give us capital B, and then finally the amplitude is the distance from the minimum value to the maximum value, which is 2. Okay, so the period equaling 1. Well, that means that 1 has to equal 2 pi over, so with the period equaling 1 has to equal 2 pi over capital A. You can always pick your cycles so that you can always avoid any reflections. So A and C, when you're starting with the graph, you can always fix it in such a way so that A and C are always positive. When you go and solve for A, you're going to get that A has to equal 2 pi. Okay, now the midline being -1, that gives you capital D is -1. I'll actually switch colors as I write some of this stuff down. Okay, so we said A had to equal 2 pi. We said D had to equal -1. The phase shift being 0 units implies B equals 0. And the amplitude being 2 implies that the vertical stretch factor is positive 2. So now h of theta, okay, that's the given graph, is going to be 2 cosine of A times theta minus B. Since A is 2 pi and B is 0, you're just going to get a 2 pi theta, and the midline being -1 meant D is -1. Okay, so there's a model for this graph. Okay, the function in the function of this graph in algebraic form is 2 cosine of 2 pi theta minus 1. Couple comments. You could have also found a cycle of this graph that looks like sine. So I won't go through it. The only thing that would change there would be the phase shift, so you'd still have the same amplitude, midline, and period, so the same capital A. Just to illustrate, okay, I could have, let me fix my midline again. I could have seen a cycle starting at the middle value on the midline that has the same shape as the graph of sine. The only difference is your phase shift would be minus 0.25 units to the left. So you would use all the same parameters except your capital B would be negative 0.25. And then instead of using a transform cosine, you would do a transform sine. Okay, so one more example of an application problem where we're going to model your height on a Ferris wheel as a function of time using a transformed sine or cosine function. Okay, so example 8, modeling height on a Ferris wheel. So suppose you're about to ride a Ferris wheel at an amusement park. The Ferris wheel from the bottom to the top is 150 feet tall. That would correspond to the diameter of the Ferris wheel. It takes 2 minutes to make one complete rotation. Assuming the height above ground of the Ferris wheel at its lowest point is 3 feet. Find a function h of t that models your height t seconds after beginning a rotation. Okay, so a couple important things. First, the Ferris wheel is 150 feet tall. It takes 2 minutes to make a complete rotation. Okay, and the height above ground at its lowest point is 3 feet. Okay, so I do this in kind of a 3-step process. First, I like to draw a picture of my Ferris wheel and illustrate my heights and times for, well, quarter rotations, just like we always break up the period into fourths. Okay, so imagine this is, oops, that's not a horizontal line. So this is ground level, your Ferris wheel slightly above ground. The distance from the Ferris wheel to the ground is 3 feet, and the distance from the bottom of the Ferris wheel to the top is 150 feet. Okay, right down here, this is where you're going to start your ride. Okay, so this would be t equals 0 seconds, and there your height is going to be 3 feet. A quarter of the way through the rotation, which would be after 30 seconds, your height is going to be 3 plus the radius of the Ferris wheel, which is 75, so you get a height of 78. At the top of the Ferris wheel, so after t equals, now here you would be half the way through the rotation, this would be 60 seconds. The height is going to be the 3 feet plus 150, which is 153. 3/4 of the way through your ride, which would be after 90 seconds, your height is going to be, again, 78 feet. And then again, when you get back to 120 seconds, that's supposed to be a comma right there, not a decimal. So at 0 and 120 seconds, your height will again be 3 feet. So what you're going to do, and sorry that picture's a little bit cluttered, but I'm going to use those input values, which would be the time, and the outputs, which would be the height, to now sketch a graph of our function. Okay, so I need a vertical axis. I don't really need much in the way of negatives. This is our t-axis. Okay, let's say here's one period, that's 120 seconds. 2 periods or 2 rotations is 240. Okay, and then we have 60, 30, 90. And then we'd have, let's see, halfway through this would be 180. This will be 210, and this right here would be 150. Okay. I'm going to put a break in the graph. Our graph is going to start at 3 feet. Our maximum height is going to be, so this is the h-axis, this is 153, and halfway between those is 78. That actually ends up being your midline. Okay, so there's my midline, and then I'm just going to plot the points that we get from our picture of the Ferris wheel. Okay, so let's see, let's use blue, a good shade of blue. You originally at 0 seconds start at a height of 3 feet. After 30 seconds, you're halfway up at 78. After 60 seconds, you are all the way up at 150. After 90 seconds, you're back at your middle height. And then finally, after a full rotation, after 120 seconds, you're back down here. So the first cycle is going to look like this, or that could be viewed as one cycle. And then another 30 seconds through, you're back at the middle height. Another 30 seconds, you're at the max height. After 210 seconds, you're back at the middle height. And then finally, through 2 rotations, you're back at a height of 3 feet. So that's what the graph would look like of this function modeling your height on the Ferris wheel, where t is in seconds. And what I'm going to do, and you can do this in either way, I can either find a cycle that looks like the fundamental cycle of sine or the fundamental cycle of cosine. Okay, so let me get my red back out. Let's just do this with cosine, for instance. So I start up here at its max value, I come down to the minimum and increase back to a max. So that piece looks like a fundamental cycle of cosine. Okay. Now, below my Ferris wheel over here, that fundamental cycle, that looks like a cosine, okay, that cycle starts at 60 seconds. Okay, so number one, the phase shift is 60 units to the right, so B is going to equal positive 60. 2. I need the period. The period is going to be the 120 seconds, which is supposed to be 2 pi over capital A. If you solve for A, you're going to find out that A is equal to pi over 60. Okay. 3. The amplitude is the radius. The amplitude equals 75, so that tells me that C has to also be 75. And then lastly 4, since the midline is 78, that gives me my vertical shift. Okay, so capital D is 78. Now if I get rid of my picture of the Ferris wheel here, my function h of t that models my height, it's going to be the capital C, which in this case was just the amplitude of 75, times cosine of, since the period was 120, we solved for a and got pi over 60. In the parentheses here, I should have my input variable this time is t minus the phase shift, which was given by 60, and then plus the middle value of 78. Okay, so there is a function that models your height on the Ferris wheel as a function of time t in seconds. And I could have also found a cycle in the graph again that looked like the fundamental cycle of sine, and came up with a model that was a transformation of the sine graph. Again, only thing that would change there would be the phase shift. I think in that case, if you would use sine, you can see a cycle that looks like a graph of sine would begin at 30 seconds. So everything would be the same except the cosine changes to sine and the 60 phase shift changes to a 30 phase shift. Okay, so that's everything I have here. That gets us through section 4.3. More video, I guess a video for section 4.4. I might post one either on Friday morning or Monday morning next week. I also might, well, I did indeed get a webcam, so I might start also recording the class sessions rather than making these videos by hand. So just stay posted. Thank you everybody for tuning in. And if anybody has questions, make sure to either come to my office hours in the TLC at 1:30 to 2:30, or find some time to set up an appointment with me. Alright, thank you.